Okay, everybody, welcome to a series of videos that I'm going to be putting out on chemistry, and a lot of it is going to be learning chemistry. Um, this first video is actually going to be about the periodic table of elements and what it is, and how to identify some special things about it, such as atomic weight, number of protons, electrons, what each single family, what each single period is, etc. And this course is actually going to be designed to follow the FLVS uh, coursework and criteria, because I myself am an FLVS student. So if you're in the Florida area, this will be, more lenient towards you because this is the kind of stuff that I learned. If you're from another state or from another country, the concepts will be pretty similar. Um, so let's get started. So what is the periodic table of elements? Well, imagine it like a showcase of everything that makes up everything. So what are elements? Elements basically make up everything that we look at. Salt, sodium chloride, that's Na plus Cl, sodium chloride. Let's take water, H2O, and oxygen is right here. Bunch of things like gold, platinum, everything you can think of. So let's get started by analyzing what each of these columns mean. So what is a column on the periodic table? Let's take a look right here. So let's take from right here to right here. And we're going to exclude hydrogen in this. So let's go ahead and cross this one out because hydrogen is a very special element. Yeah, there's a very special reason it is in this column. But it is very dissimilar to these properties. So let's take a look at each one is called. So each column is actually called a group or a oh, I don't know what it is there, but it's group or family. I know my handwriting is kind of bad because I'm doing this with a mouse. Family. Okay, so each one is a group or a family. So let's from lithium to francium, this is one group or family. From beryllium to radium, that is one family. From titanium to rutherfordium, that is one family. These are actually kind of special. These are called the transition metals. This is like your iron, your cobalt, your nickel, your gold, your silver, etc. Then you also have your lanthanides and actinides, but I will talk about those later. Let's go ahead and talk about what each family is now. So I'm pretty sure a lot of you know that families share common properties. And if you didn't know that, word of advice, and it's very important, so make sure you write this down in your notes. Families share common properties. And what do I mean by that? Let's take lithium, sodium, potassium, rubidium, and cesium and francium, for example. Um, these will use each column will each have a specific name to it, except for the transition metals and a bunch of these special things. So let's take these orange things are called alkali metals. Alkali metals are very, very reactive to other substances. That's why a lot of you have heard of lithium-ion batteries. That's why they say not to break those open or not to throw them away because they can be potentially really harmful to the environment. Sodium, you wouldn't think it, but it is actually very reactive. If you've ever seen sodium metal, that will actually explode if it comes into contact with certain substances. I think water is one of them. Potassium, those are inside your bananas, so just remember that. Bananas are very dangerous. I'm just kidding about that. Bananas are fine. It is because it is mixed into a lot of other substances. So these metals are very reactive, and also keep in mind that these are all metals right here, from orange to yellow to whatever color this is, like light pink, to about blue. And I think these ones are excluded, but don't quote me on that. So let's go ahead and talk about these yellow metals. What are these yellow metals? Well, they're very similar to the alkali earth metals, but these are called the alkaline earth metals. Now, what's the difference? Well, the main difference is that these are actually a little bit less reactive. And I also didn't mention this earlier, but alkali earth metals and alkaline earth metals are so reactive that they usually do not appear in pure substances on Earth. They normally appear in compounds. So let's take magnesium, for example. You normally would not have a pure sample of magnesium because it is just so reactive. You would usually have it inside something else. A common example would be milk of magnesia. Another one is sodium chloride, like I said earlier, with the salt, Na plus Cl. You normally would not find this by itself, since it is so, also, since items are so reactive that they're constantly going to be trying to bond with other metals, and that's what I mean by reactive. Um, so yeah, basic things to take away from that is that these are super reactive, and since they are so reactive, they do not appear in pure substances, unlike, of course, iron and cobalt and nickel. Let's go ahead and talk about these transition metals. These transition metals are usually the most abundant in Earth's crust, for example. Aluminum is very special because it belongs in this group. The only reason it belongs here is because of electron configuration, um, and other things too. And you can also look at uh, the diagram down here. We'll be talking about this a little bit later, and it will discuss the atomic weights and atomic numbers. But for now, let's keep talking about this stuff. So, um, let's take an element, for example. Let's talk about iron. How is iron similar to ruthenium? I don't know how to pronounce that. It's been a while since I've seen that element. So basically what happens is that you have each of these families, right, that I talked about earlier, and these share common properties, like I stated earlier. But transition metals are a little bit more special because they have their very own ionic charges. And normally you wouldn't find a pure sample of iron by itself, unless you were working with tools or something like that. Um, but you would usually have iron oxide or something like that, and then that changes your ionic charges. And I would also talk about that a little bit later. There's actually a diagram of the periodic table which states every single ionic charge, so you can tell when you make those compounds. And I again will talk all about that later. Just make sure you take away the important stuff that I'm talking about here, like families share common properties, like I have over here, super small. I'll zoom in once again so you guys can look at it. Um, and also, let's these groups. So we have alkaline earth metals, transition metals, and now we're going to start talking about the poor metals. Um, Poor metals is another word for special metals. So we have mercury over here. I'm sure a lot of you have heard of mercury. Mercury is a liquid element pretty much at room temperature, which is very strange when you're talking about metals here, because usually when we talk about metals, we think of something hard and not very malleable and very shiny, unless you're talking about gold, which is very malleable. So we can also see that these elements would share their common properties. Um, and something interesting is that you might see these unumbrium, ununtrium, unquantium, or something like that. Um, these elements are actually elements that have not been discovered yet, but thanks to our handy-dandy scientists, we can infer that these elements would have the same common properties as these columns. Sorry, I'm just feeling a little bit under the weather today, but yeah, so we can infer, and actually, scientists have found what each of these elements are. I'm actually using an outdated um, uh, periodic table. So I'm going to say right here, stupid, even though this is not stupid. I'm just saying that because these are actually found. So I'm guessing this table is from, I want to say 2015 or early 2016. These elements were actually found in June of 2016, if I remember correctly. let's go ahead and start talking about our other nonmetals. So what are these? If anyone wants to take a guess at this, let's look at oxygen, for example. I'm sure a lot of you know that oxygen is only present as a gas. Um, uh, in the atmosphere, I'm trying to say, and that's the most common form that people would think of is oxygen in the air. We need it to breathe, we need it to live, all that fun stuff. But basically, what oxygen is it's a non-metal, which means it doesn't share the same properties as one of these metals. Um, most of these are gases. If you look right here, at room temperature, uh, you can look at these sort of indicators that will tell you what they are. So these at room temperature would be gases. This at room temperature would be a liquid. This at room temperature would be a liquid. And then all these, the ones that are black, would be solids. Let's go ahead and take a look at our final column. And these are called the noble gases. Noble gases, I'm pretty sure a lot of you have heard of them. Neon, a lot of neon is used in neon signs. Helium is used in a lot of our balloons. That's because it's less dense in the air. Hydrogen, and now we start talking about this over here, even though this is not a noble gas. This is a very special element, like I'm trying to say, like I was saying earlier, and it also exists only as a gas in most forms, unless it's bonded to another element, such as oxygen. That might seem a little weird to you, how hydrogen, a gas, plus another gas would equal a liquid. Well, I will get into that a little bit later, like I said. Um, what is these special two rows down here? Well, I'll talk about them in a little bit. I won't forget about these. This will be in this video. But first I want to talk about these numbers. Now, what are these numbers? Does anyone want to take a guess at it? Well, the word is right here. Periods. So, no, not like the woman just fancy stuff. This is the things that will give our periodic table its name. Periods, if I could spell. Okay, so what are periods? Well, periods essentially go row by row. And I'm pretty sure a lot of you have seen these numbers down here and here and here and here. Well, our periodic table is actually going up horizontally. So you start out with hydrogen, which has an atomic number of 1, which then moves to 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then it just keeps going on and on and on till 118, and then you have your special ones down here, etc. And that's also what these numbers mean. It's actually a gap between here and here. So if you have 56, then 57, all the way to 71, 57 to 71, then you have 72 again. So, sorry for that. Let's go ahead and look at what each period represents. Well, normally, going left to right, these atomic weights will also be increasing. So let's look closer. Actually, we can look at the bottom graph, and this is exactly why I grabbed this graph. We can look at these atomic weights, and atomic weights are essentially how heavy that particular element is in terms of grams per mole. So we can see that as you go left to right, you go from 1 to 4 to 6 to 9 to 10 to 12 to 14 to 15 to 18 to 20. There really isn't any order in which they increase. It's more of that they are increasing from left to right. We can also find that down here we also have a break. So if you go 137 to 138 or 137 to 138 to 173 to 174. So everything is very connected. The reason we call this the periodic table is because the periodic table is actually periodic. And that means that as you keep going left to right, eventually the properties start to resemble themselves. And that's what I mean by families share common properties. Um, Basically, what had happened is when Mendeleev, the founder of the periodic table, as many like to call him, is he determined that elements, as they keep going, are essentially periodic. Um, we know that as you go on, eventually these properties will be similar. Well, Mendeleev, what he had to do is go against everybody, which was saying, oh, you should keep it going in order from least atomic mass to most atomic mass. You should keep it that way, right? But what he said is, no, we have to do it this way, where essentially they're arranged in periods. So he had a very bold idea, but that's what we use today. And actually, we like to call him the founder of it, and he also set basis for a lot of the elemental researches we have today. So, what else is there to talk about besides these? Oh yeah, let's talk about these numbers. So, let's take oxygen for example, and I'm sorry for the resolution, it's a little bit low. So, oxygen. What is oxygen? Well, we know it's an element, right? We know it's an element, and it has an 8 on top and a 15.999 at the bottom. So, what does this mean about the element? This means that this element has an atomic number, right? We call this the atomic number of 8. So oxygen has an atomic number of 8 and atomic mass of 15.999, or simply 16. So what is the atomic number? Let's talk about that one first. Well, the atomic number is the amount of protons and electrons found in the most stable isotope of the element. So normally, oxygen has 8 protons and 8 electrons. Um, this number down here is called the atomic mass, and we already said that. But what this is, like I said earlier, is a measure of how heavy this specific element is, and this is 15.999 grams per mole. And I'll get into molar concentration and molar mass and everything like that later. Um, just remember that this is in grams per mole. So this is 15.999 grams of oxygen per moles of oxygen. So what does this number mean? This means that this is how heavy the element is, as I said earlier. But this also means what isotope this is. Like this is oxygen, but this has an isotope of a mass of 15.999. Or simply 16, because normally we wouldn't go this far into it. But when you're talking about super specific and accurate things, you need to start talking about these little things like that. Like right over here, let's look at forgot which one. I think this is No, that's not silicon. This is sulfur. How could I forget that? This is an atomic weight of about 32, but it says 32.0666 or 66. Um, Basically, our atomic mass can be used to find out the number of neutrons. And we all know that we have a nucleus of an atom with electrons orbiting around the nucleus. So we have little protons and neutrons that are gathered up in the center, and then we have electrons orbiting around. So this is not an accurate diagram. This is just kind of like a makeshift diagram. But so since our atomic number tells us how many protons there are, and it tells us how many electrons there are, it should also tell us how many neutrons there are. That's not correct. We can actually determine that from our weight. And this is why we have the weight on the periodic table, is to also determine how many neutrons there are. So if we take the number of protons, add them with the number of electrons, and we should get ourselves the atomic number, and that is the number that we have right over here or here. This number, let's take 16, right? I don't know why it just did that. 16, right? And that is going to equal our atomic mass, right? So, if our atomic mass is 16, and we have 8 protons and 8 electrons, we can actually determine how many neutrons there are. So if we take 16, which is our atomic mass, which is how heavy the element is, minus the number of protons, that will give us our number of neutrons. And this, simplified, would be 8, right? So we have 8 neutrons, 8 protons, and 8 electrons. And we can just determine that by looking at the atomic symbols or atomic elements themselves. So let's go ahead and talk about isotopes. So isotopes are basically the same element with the same number of protons, same number for electrons, but different masses. So now the most common one that people talk about are uranium-232, uranium-238, and this basically means that its atomic weight is constantly changing because it is radioactive and is constantly giving off these particles. So all this information might be a little bit hard for you to grasp. This is also my very first video that I'm making on this, so I hope a lot of you guys are nice, decide to share this with your friends, and decide to watch these videos and try to learn. And that's what I'm here for, is to help you guys learn. So if you have any questions, please, please, please leave them in the comments below. If you also want to see a different video on the same subject, like oh, that was my watch. If you guys would like to see more on molar masses, calculations, stuff like that, if you need help on FLVS homework, if you guys need help on any kind of chemistry homework, please, please, please leave it below. Please, I mean, not to brag or anything, but I am pretty familiar with chemistry. I mean, I think I'm doing pretty well in the class currently. But please leave any comments you have in the comment section. And yeah, that's pretty much it for this video. And these are the basic concepts for the periodic table of elements. Thanks.